Students, today we are going to study about racemic mixture and rasmization. Racemic mixture and racemization. So the very first term is racemic mixture. What does this means? Racemic mixture, or it is also called racemate. Racemate or your racemic mixture is an equimolar mixture of two enantiomers. Let's say we have a compound which have a one chiral center, so there is a possibility of obtaining two different enantiomers, one which rotates the light towards left side, other one which rotates the light to the um, reverse direction. So that ways we will have two enantiomers, one will be dextro rotating, other will be levo rotating. So racemate or racemic mixture is an equimolar mixture of two enantiomers. All right, this is the definition. Now since racemic mixture contains the equal number of dextrorotatory molecules and levorotatory molecules, so the net optical rotation will be 0. So let's write down some points. It will have equal number of dextro rotating and levo rotating molecules. Therefore, net optical rotation is 0. All right. And if we have to symbolize that we have a certain compound or we have a certain solution which have equal amount of both the enantiomers, so we write this symbol in front of the IUPAC name, that is plus minus within small brackets, or DL within small brackets. This symbol we use to symbolize the racemic mixture. Okay, so this is what is racemic mixture. Next thing is rasmization. Now rasmization is the process by which a pure enantiomer is converted into the racemic mixture. Okay. Or you can in symbolic form you can write, if you have a plus enantiomer, it will be converted into equimolar plus minus mixture. Or you have -1, then that is also equally converted into plus and minus. Okay. Now how the racemization is done? There can be many processes. First of all, very simple is physically, if you mix simply by mixing equal amount of two pure enantiomers. Let's say you have both the enantiomers separately. You take equal amount of both the enantiomers and mix them. That will give you a racemic mixture, or you can say the racemization is done physically. But that's not the case always. You do not have all like both the enantiomer present with you. So in those cases, what can be done? So there are some chemical ways also. If you have to do something chemically, let's say you perform some reaction, you take a starting material in such a way and proceed with the reaction so that you get a mixture of two different enantiomers in equal amount. So let's take an example. I'm taking 2 butanone, 2 butanone. So if we write the structure, it is CH3CO CH2 CH3. So this is a achiral molecule. It doesn't have any chiral center. So let's do the addition of hydrogen gas, H2 addition. If you do the H2 addition, since it's a planar compound, so what will be the geometry? Geometry is sp2. sp2 hybridized, that means you have 3 different bonds. Let's say this is carbon carbon double bond. This pen represents the carbon carbon double bond. This represents your ethyl group and this represents your methyl group. Okay, if we consider this carbon as this point, then this is your carbon oxygen double bond, this is ethyl, this is methyl. Okay, now you have to do the addition of hydrogen. Okay, so there is a possibility that the attack takes place from this side or the attack takes place from the bottom side. So due to the equal possibility of attack, equal amount of both the enantiomers will be formed. Okay, so the carbon atom, this carbon atom will have these two groups attached and these were already there. So if you see now, this carbon is a chiral carbon. This carbon is a chiral carbon and it will have both the enantiomers in the equal amount. Okay, so the two enantiomers are formed in equal amounts. This is chiral molecule and two enantiomers are formed in equal amounts. So it is racemic mixture. Okay, so this example that I have given you is for those only for those reactions which do not have any enantioselectivity. Like sometimes there are some molecules which will have some kind of steric hindrance, and due to that hindrance the attack from both the sides above and below the plane of the molecule is not equally possible. एक साइड में hindrance होगा तो the attack from one side will be dominating. So in some reactions you might get one one enantiomer in majority, other one in as a minor product. So in those cases you will not get a racemic mixture, or sometimes only the attack from one side is possible, other side the attack is not possible at all. So in those cases you will only get one enantiomer. So those reactions are called enantioselective reactions. So this particular reaction I have given, this is not at all enantioselective. The attack is possible from both the sides. So you are getting a racemic mixture. Now if we take the examples of let's say some particular reactions which involves the formation of your enantiomers. I'll give this topic a heading A. Okay, so we will discuss some different kind of reactions in which formation of enantiomers takes place. Formation of enantiomers takes place, or let's say those reactions in which a stereo center is generated. So the generation of stereo center can be uh, from the free radical mechanism, or let's say cyclic uh, intermediate is being formed, or a carbocation is being formed. So first of all we are taking mechanism which involves a radical intermediate formation. So the very basic reaction that we study is bromination. This is the first reaction you ever study in the mechanism of free radical reactions. So we are taking example of bromination of let's say butene. Okay, so not butene, butane. Butane we are taking. So if I have to write down the formula, it is CH3, CH2, CH2, CH3. Okay. I am writing this in the form of dashed and wedge formula. So these two are the same, this and this. Okay, now you can clearly see that this is a achiral molecule. Okay, this achiral molecule, when it undergoes bromination from free radical mechanism, a Br radical will attack on this butane, and what happens, the other radical removes the proton radical, so the one HBr will be removed. Okay, the first of all the HBr is being removed, so you will get a free radical intermediate. Okay, so this carbon will have methane and ethane, this carbon will have a free radical present on it. Okay, now this is also a achiral radical. This is not a chiral molecule. This is also a achiral radical. Now what is the possibilities? What happens now? The Br2 molecule will attack, or you can say this radical will attack a Br2 molecule. There are two possibilities, that the Br radical joins from below the plane or above the plane, similar to the addition of hydrogen that we discussed in case of butanol. So what happens, these two lobes of the radical are equivalent. These two lobes are belongs to p orbital, so these are equivalent. So attack can equally likely from the top or bottom phase, and that will give us a racemic mixture. So let's see if the attack happens from below the plane. So what you will have, your bromine will be added at the bottom. Okay, CH2, CH3 will be towards the Weaver. Your methyl group will go away from the Weaver, and your hydrogen will be in the same plane. So this kind of attack happens. So what is happening? The attack is happening from this side. This side the attack is happening. So this kind of product will form. If the attack happens from that side, the product will be formed as your Br will come on in the same plane, hydrogen, your CH2, CH3 will be toward the Weaver, and your methyl group will be away from the Weaver, and a Br radical will be removed. Okay, so what we have? We have two different enantiomers. Let's see the RS nomenclature here. So if you could see the least priority group, if you have to assign the priority, Br will be the first priority, this will be second, this will be third, this will be fourth. These priority assigning we have already discussed when we did the RS nomenclatures, right? So if you see the rotation is anti-clockwise. Okay, rotation is anti-clockwise, but there is a glitch. Your least priority group is towards the Weaver. So instead of writing it as S, you will write it as R. So the name will be R 2 bromo butane. Okay, this will be the IUPAC name of this molecule. Let's see the second molecule. Again the priority order will be same. Br will get first, CH2, CH3 will get second, CH3 will get third, and hydrogen will get fourth. And if you see the rotation is anti-clockwise. Rotation is anti-clockwise, and again what is happening? Okay, since I have not taught you the assigning of notation in this wedged and dashed form, so what you will, how you will assign, see the example here. You could clearly see my fingers. So this thumb represent the ethyl substituent. This represents the methyl. This represents the bromine. Okay, and the hydrogen is, let's say, my hand. Okay, when you have bromine, this is bromine, so this is your first priority, this is your second priority, and this is your third priority. When you're seeing the rotation is anti-clockwise. 1 2 3, rotation is anti-clockwise, but when you are viewing it from this side, okay, when you are viewing it from this side, your hydrogen is away from you. So in that case, you do not have to worry whether your hydrogen, when you are drawing it on the paper, it is in the plane of the molecule, or away from the Weaver, or toward the Weaver. You just imagine it in a 3D. So in 3D, when you are viewing it from this side, this where my pen is there, that way you can see the rotation is anti-clockwise and your hydrogen is away from here. So you can simply assign the RS nomenclature, and for anti-clockwise it is S. So it is S2 bromo butane. If you want to do the nomenclature for this one, it is also the same way. Okay, so these three, now my thumb will be bromine, and this finger will be ethyl, and this finger will be methyl. So the priority order will be 1 2 3. Okay, 1 2 3. So that way you can imagine the rotation, how you are going to do the rotation. Okay, and you can assign the nomenclature. So this was the one example in which the mechanism was involving radical intermediate, and there was a possibility of formation of both the enantiomers in the equal amount. So here you are getting racemic mixture. Okay, here racemic mixture is obtained. And discuss if we discuss the second type of mechanism, that will be uh, mechanism involving carbocation. Before that, I would like to tell you one thing. Here we have these two hydrogens. These two hydrogen, if replaced by any other functional group or any other substituents, the molecule obtained will be chiral. So the hydrogens present on the second carbon of the butane are called enantiotopic. So you can say these hydrogens are enantiotopic because on replacing these hydrogen, one of these hydrogen by any other group other than methyl, ethyl and hydrogen, you will obtain a achiral center here. So if you see, there are 4 enantiotopic hydrogen in the butane. These 2 hydrogens or these 2, any of these 4 hydrogen can act as enantiotopic hydrogens. Okay, so remember this word, enantiotopic. Now this is the second mechanism, that is mechanism involving a carbocation. Okay, so if we are discussing a carbocation, let's take an example of addition of HBr to 1 butene. Okay, so 1 butene is CH3 CH2 CH double bond CH2. So this is your 1 butene and this is achiral, correct? Now if you, we know that addition of HBr takes place via formation of a hydrocarbon. So the first of all, proton attacks these molecules and form a more stable carbocation. So there are two possibilities. One, that the proton gets attached to this this second carbon, or it can get attached to your first carbon. So first of all, we are taking in okay, no, I have already written the hydrogen here, so this should be H, sorry, this should be CH3. So first I have written, when the addition takes place on the first carbon, another possibility is your hydrogen attached to the second carbon and you get a CH2 positive. Here this carbon will have positive charge. So if you could see the two possibilities, in which one where proton attached on this carbon, other one where proton gets attached here. So you get two different kind of carbocations. This is a secondary carbocation, this is a primary carbocation, and since the mechanism is SN1, SN1 is, that means it's a two-step process. First intermediate is being formed. So the carbocation that is more stable will be formed, and we know that the secondary carbocation is more stable as compared to the primary. So this carbocation will be formed instead of this one. This will not form. Okay, so this was the first thing that I wanted to discuss. Now what happens? H positive has been attached already. Now Br negative will attach. Okay, so again similar to the free radical mechanism, here also is a possibility of bonding from either side, because we know that carbocation is also a planar entity. So the bromine can get attached from the above or from below side. So the two possibilities that we are obtaining are these. Okay. So again, if we have to assign the RS nomenclature, this will be S. You will be practicing this RS assigning for these molecules. Either you imagine the molecule in 3D and then you assign the RS nomenclature, or you convert these to the Newman projection or Sohos, or whichever projection you can clearly assign the RS nomenclature. So the conversions you will have to practice. So this is S2 bromobutane, okay, and this is R2 bromobutane. So the possibility of formation of both the enantiomer is equal. So here also you are getting racemic mixture. Okay. So now if we have to see the another mechanism that you might not have studied, it is if the product involves epoxidation. Okay. So in that case also there is a possibility of obtaining a racemic mixture. So third is your mechanism involving cyclic intermediate, or you can say cyclic products are formed. So let's take the example of 2-butene. Now 2-butene is that it has two possibilities. It could be a trans or it could be a cis. So if you write the molecule something like this, this is trans, this is your trans 2-butene, and if you write it as this is your cis 2-butene. Okay. So first of all, we perform the epoxidation on trans 2-butene. Now we have discussed two different kind of nomenclature in case of alkenes. One was cis trans, other one was E and Z nomenclature. Now there was one thing that I forgot to mention during that time. You can also write the cis trans names in terms of EZ. The molecules that can only be written into EZ cannot be written as cis and trans, or you can say where you have three different substituents. Those cannot be right in terms of cis and trans, but the molecules which will have only two different substituents, those can be written as E and Z. So if you have to write the EZ nomenclature for these two molecules, here we have both the same kind of substituents on opposite sides. So this could be written as E2-butene also, and this as Z2-butene. So both the names are acceptable as IUPAC name. Both are correct. You can write any of these two names. Okay. Now let's proceed with our epoxidation. First of all, I am taking the trans this is trans 2 butene, or you can say E2 butene. Now epoxidation is performed, and in order to do the epoxidation we are taking a percarboxylic acid. Okay, so this is percarboxylic group. Okay, this provides the nascent oxygen and hence results in the formation of epoxide. Epoxide is this kind of group is called epoxide. Okay, so the possibility of epoxide formation is from both the side. The epoxide or nascent oxygen could get attached from that side, like above the plane, or it could get attached from below the plane. So if it get attached from below the plane, the possibilities are something like this. Okay, so now there is a restriction in rotation because of the cyclic part. So these two are actually racemic mixtures. Okay, the compound form is trans 2,3 epoxy butene, sorry, butane, epoxy butane. Okay, and it's a racemic mixture. So if you have this kind of reaction, you will obtain the racemic mixture. But similarly, if we see the cis analog of the same compound, cis 2 butene, epoxidation is performed. Similar kind of reaction conditions you have to provide. So what will happen? Either you do the attack from the above the plane or below the plane, your two hydrogens will always be on the same side, either away from the weaver or towards the weaver. That depends from which direction you are watching. Okay, now if you could see, there is a plane of symmetry here. If we cut this molecule from this dashed line, we will get two equal parts of the molecule. So this is not a racemic mixture, instead it's a meso compound. It's a meso compound obtained. So it will be cis 2,3 epoxy butane. Some of you might have a confusion. Okay, some of you might say that if we, so here what is happening, if you are doing the addition from above the plane, you will get this kind of product. But if you are doing the addition from below the plane, you should get a molecule like this. Okay, so how these two are similar? Okay, this could be a confusion. Now what actually is happening is, these methyl groups are above the plane. They are you have this triangle on the plane of the paper. ये पेपर के ऊपर है, and these two methyl groups are pointing like this, पेंसिल के जैसे ऊपर में 90 डिग्री का एंगल पे खड़े हैं. ठीक है, and the hydrogens are actually below the plane of the paper, ये नीचे में है. That's why we have drawn the dashed lines. Okay, अब this is actually on the plane of paper. ठीक है, अगर हम इस ट्राइंगल को पकड़ के 180 डिग्री से रोटेट कर देते हैं, 180 degree से if you rotate this triangle, so what will happen, ये flip हो जाएगा and you will get a something like this. ठीक है, लेकिन जब हम triangle को flip कर रहे हैं, then the groups attached will also be flipped. ठीक है, वो भी flip होंगे. The methyl groups will which were earlier pointing above the plane, they will go below the plane, and the hydrogens will come above the plane. Okay, so that kind of structure will be obtained. And if you see, it's nothing but the same, these two will be same, so it's a meso compound. So till now we have seen two things. One, when we were physically mixing two different enantiomers in equal amount to obtain a racemic mixture. Second, we took some kind of starting material or a reactant, and we proceed with the reaction, and the products obtained were actually a mixture of two different enantiomers, or you can say racemic mixture was obtained as a product. Now third thing is, if you have a single enantiomer, so if you have to do Rasmization from one enantiomer, so in some of the cases this is possible. There are some molecules which show Rasmization or which show optical activity due to restriction of rotation about a single bond. Okay, so let's take the example of by rotation about a single bond. So if we have to see such kind of molecules, biphenyls, what kind of compounds are these? Two benzene rings are bonded with each other by a single bond. Now these two benzene rings are not like this. तो benzene ring बराबर बराबर में नहीं होती है. What happens if this benzene ring is some like this, other one will be tilted. This will be due to the steric hindrance, or sometime you have some kind of substituents. Let's say it has COH, and some other bigger group is attached on this side. Let's say C3H7, something like that, and similarly on this side also. So instead of having these two benzene rings in the same plane, they will get twisted. Both of the rings will get slightly twisted to reduce the steric hindrance. So those kind of molecules will show the optical activity. They will have a restriction around this single bond, so they will be showing us the different enantiomers. Okay, so if you provide enough thermal energy, आप उसमें heating करते हैं, तो what happens, that energy barrier, this energy barrier of rotation around this single bond is achieved, and the compound rotates, वो flip कर जाता है. So if you have one enantiomer, let's say if you have a dextrorotatory enantiomer of this biphenyl, so on heating it, what will happen, that some molecules will flip, and you will obtain a racemic mixture. आपको डेक्स्ट्रो लीवो दोनों मिल जाएंगे उस केस में. So the first thing is by providing enough thermal energy to overcome the energy barrier to obtain the racemic mixture. So this is one type. This is one kind of flip I am talking about. Another thing is, if you see the sugars, आपके sugars में क्या होता है, you generally have cyclohexane, right? तो अगर वी आर नॉट टेकिंग सब्सटीट्यूएंट्स ऑन ऑल द कार्बन एटम, हम कोई दो पे ले रहे हैं, ठीक है. So this hydrogen is this hydrogen is present on the equatorial position, while this hydrogen is present on the axial position. Okay, so if you have to provide the numbering, if you see, let's say this is the first carbon, this is the second carbon. So what happens if the hydrogen is present in the equatorial position? That means it is away from the weaver. Okay, and if for this carbon, if you see, this is the first priority group, first priority carbon, this is second priority carbon, this is third priority carbon. So the rotation is your clockwise rotation. For clockwise rotation, your RS nomenclature will be, you will be assigning it as R. Similarly, if you see this is axial position. Axial position, that means the hydrogen is not away from the weaver. It is actually on the plane of the paper. So you can say it is the least priority group is not away from the weaver. So when you are assigning the priority here, 1, 2, 3. So the rotation here is anti-clockwise. If you imagine it in the अपोजिट डायरेक्शन, आप दूसरी साइड से अगर देखते हो तो आपका रोटेशन क्या है, आपका रोटेशन एंटी क्लॉकवाइज है, एंड इन दैट केस यू विल बी प्रोवाइडिंग द नोमेनक्लेचर एज एस. ये एस हो जाएगा, ठीक है. अब अगर आप इस रिंग को फ्लिप करते हो, साइक्लोहेक्सेन्स क्या करते हैं, रिंग फ्लिप होता रहता है ना, there is a very small energy barrier and the ring keeps on flipping. ऐसे flip होता रहता है. If you provide enough energy, this ring will flip, and this carbon will come on this side. मतलब ये जो कार्बन, let's say this is number 1, this is number 2, 3, 4, 5, 6, तो ये कैसे बन जाएंगे, 1, 2, 3, 4, 5, 6, ऐसे कन्वर्जन हो जाता है, ठीक है. तो इफ़ वी हैव टू राइट दिस मॉलिक्यूल इन इट्स फ्लिप्ड फॉर्म, तो ये कैसे बनेगा, रिंग फ्लिप होगा एंड यू विल गेट अ मॉलिक्यूल, ऐसा बनेगा, ठीक है. इस पे ये मिथाइल ग्रुप जो, व्हेन द रिंग फ्लिप्स व्हाट हैपेंस, the groups which are present on the axial position will go on the equatorial, and the equatorial groups will come on the axial position. So this is your first carbon and it has two substituent, one hydrogen and other one methyl. Methyl was present on the equatorial position, so you will write it on the axial position, and your hydrogen will come on the equatorial position. Okay, something like this. For second carbon, your methyl group was present on the axial, so it will go on the equatorial, and hydrogen will come on the axial position. So now if you see, now if you check the RS nomenclature, the nomenclature will not change. Okay, the first carbon will remain S, second carbon will remain R. You, when you are flipping the ring, you cannot change this configuration. आप उसको नहीं change कर सकते. So if you rewrite this structure, अगर हम इसको थोड़ा सा change करके लिखते हैं, let's say we write this carbon as first and this carbon as second, तो हमें क्या करना है, हमारा first carbon पे our methyl group is on the axial position, and our hydrogen is at the equatorial position, and for second carbon our hydrogen is at the axial position and our methyl group is at the equatorial position. और आपका जो आर एस है वो क्या रहेगा, फर्स्ट वन विल बी एस, द सेकेंड वन विल बी आर, ये नहीं चेंज होगा. सो इफ़ यू कंपेयर दीज टू मोलिक्यूल्स, अगर आप इन दोनों को कंपेयर करते हो, व्हाट आर दीज आर एक्चुअली मिरर इमेजेस. आपको ये दोनों मिरर इमेजेस मिल रहे हैं. ठीक है, मिरर इमेज मिल रहे हैं. दैट मीन्स इफ द वन structure is dextro-rotatory, तो other one will be levo-rotatory, right? क्योंकि आप कुछ भी bond break या form नहीं कर रहे हो, you're just changing the you're just flipping the ring, और flip करने के बाद you're getting a structure which is the mirror image of the first one. तो अगर आपको ऐसा कुछ मिल रहा है, that means you're getting a racemic mixture just by overcoming the energy of flipping the ring. आप यहाँ पे क्या क्या रिंग फ्लिप हुआ आपका. ठीक है, रिंग फ्लिप में आपको बहुत थोड़ा सा एनर्जी प्रोवाइड करना पड़ता है. दैट कुड बी ओवरकम बाय, लेट्स से आपने हीटिंग प्रोवाइड किया, और इन सम साइक्लिक कंपाउंड्स दिस प्रोसेस इज ऑलवेज अंडरगोइंग. बेंजीन, जब आपका कोई सब्सटीट्यूएंट्स नहीं होते, सिर्फ बेंजीन होता है, द बेंजीन मॉलिक्यूल कीप ऑन फ्लिपिंग फ्रॉम वन फॉर्म टू द अदर. ठीक है, तो लेकिन अगर सब्सटीट्यूएंट है, थोड़ा सा रिस्ट्रिक्शन आ जाता है. इन दैट केस यू विल हैव टू प्रोवाइड स्मॉल अमाउंट ऑफ एनर्जी. तो आपका इनएंशियोमर फॉर्मेशन हो रहा है जस्ट बाय रोटेशन अराउंड अ सिंगल बॉन्ड, और बाय रोटेशन अराउंड अ लाइक फ्लिपिंग ऑफ रिंग, ऐसा कुछ करने से. ठीक है, so this is the first kind where we can get two enantiomers from a single enantiomer. अगर हमारे पास एक enantiomer है तो उससे हम enantiomeric mixture obtain कर सकते हैं. Okay, if we see some reaction, कोई chemical reaction करना पड़ सकता है हमें. ठीक है, कोई सब्सटीट्यूशन करना पड़ रहा है, तो लेट्स राइट बी बाय सब्सटीट्यूशन रिएक्शन. Let's take an example of SN2 mechanism. SN2 mechanism is a single step mechanism. Single step, and in this mechanism, inversion of configuration takes place. All right. So let's take an example of 2-iodooctane. I'm taking 2-iodooctane. Okay, 2-iodooctane is a chiral molecule. So I am drawing one of the enantiomer. Let's see which one we get. This is first priority group, this is second priority group, this is third priority group, this is fourth is away from the weaver. If you see the rotation, it is anti-clockwise, so it is S. Okay, S2-iodooctane we have obtained. Now what happens if in the reaction mixture you have iodide ion, let's say I negative, present in the solution? So a continuous substitution reaction will be taking place. This iodide group will be removed and this will be added. Again, addition, removal, addition will be taking place continuously. It will be a single step process, so the inversion of configuration will be taking place. But for the sake of understanding, let's say we are taking this iodide as radioactive iodide. Okay, so this radioactive iodide ion, I'll write it here, radioactive iodide ion. This will form an intermediate with our S2-iodooctane. Let's see what kind of intermediate it is forming. this bond is breaking, this bond is forming, okay, and methyl group is toward the weaver and your hydrogen is away from the weaver. So this kind of this is actually representing that the hydrogen is away from the weaver, okay, and these dotted line represent the extended bond. This bond is breaking, this bond is forming. So when this iodide is lost, you will obtain iodide here, C6H13 here, and your methyl group towards the weaver and your hydrogen away from the weaver. Now this iodide is radioactive. Now if you assign the priority order, this is first, this is second, this is third, this is fourth, fourth is away from the weaver, rotation is clockwise. Clockwise rotation means R configuration, so R2 iodo octane. So what is happening here? When this intermediate state is there, there is a possibility that this bond breaks and this bond forms, but there is equal possibility that this bond breaks back and this bond forms again. So the formation of both the products, this as well as this, is there, so you will be getting a racemic mixture. So the substitution reactions involving SN2 mechanism can also provide us the racemic mixture of our desired compound, okay. There is one more possibility. If you have a, let's say, two-step mechanism. So in the two-step mechanism, we have already seen that the substitution reaction of, in case of alkene, correct? So there what you have, you were doing some addition reaction, but in the similar kind of substitution reaction, if the mechanism is SN1, so you will have a carbocation formation, and again you will have a possibility of attack from both the sides, so you will be obtaining a racemic mixture. So that way also you can obtain a racemic mixture. So this is all that we were supposed to discuss in case of racemic mixture and racemization. In the next class we will discuss something